So in this video, we're going to look at finding the domain of a function that's called a rational function, and this will be a function that we study more in depth later on in the semester. And here's the graph of this particular function, and you can see by looking at the graph that this might look like it's a little bit more difficult to determine the domain from the graph of the function. But we're going to focus on in this video is analytically determining the domain of this function. And the big idea here is that we can't have a division by zero. When we have a fraction, division by zero is undefined. So what we mean by that is if we try to define division by zero, like let's say we try to define division by something that's not zero. So 6 divided by 2, we would all agree that that's 3. And your check on the work is to multiply your denominator times the result that you get, the quotient. So we check our work by taking 2 and multiplying it by 3 and making sure that we get the 6 back. So what happens is if we try to define something like 7 divided by 0, let's suppose we want to say, I think that this is equal to 0. Well, our check on our work would be to go 0 times 0. And we would hope that it's equal to 7 if 0 is actually the answer. And clearly 0 times 0 is not 7, so 0 doesn't work if you put it here. So then you could try something else. You could say, well, maybe 7 divided by 0 is 7. So we could try that. We could say, hey, 0 times 7. But 0 times 7 is 0, and 0 doesn't equal 7, so that didn't work. And so our job is to define this division by 0. We need to figure out what to put here so that when we do 0 times question mark, we get 7. But if we multiply by 0, we're always going to get 0, and we're never going to get 7. So what we say is this division by 0 is undefined because I'm unable to come up with a value for the question mark that makes this division work. So when we're working with rational functions, what we want to understand is we can't have a division by 0 because we would get something that's undefined. So what we wind up needing is for the denominator to not equal 0. We need x squared minus x minus 2 to not equal 0. It can be any real number that it wants, but not that real number, not 0. So it's okay for the numerator to be 0. Numerator is okay because if we have 0 in the numerator, we can define it. 0 divided by 7 is 0, and the check on the work would be 7 times 0, which does equal 0, and it works. So life is good. It's definable. So numerator can be 0. There's nothing wrong with that. Denominator, no. So you grab your denominator from the rational function. It's a ratio of two polynomials. You grab the denominator and you say, hey, it can't be 0. And then you solve this. And I look at this and I say, hey, this is a quadratic. And we've already been solving quadratics this semester. We could complete the square. We could use the quadratic formula. We could try factoring it and using the zero product property. So in this case, because that leading coefficient is 1, it's worth trying to factor it. And I think this one factors if we do x minus 2 and x plus 1. And then the zero product property, if we apply it, we say, hey, x minus 2 times x plus 1 can't be 0. So for that to be the case, x minus 2 can't be 0. And here I get to use an and instead of an or because of the not equal to. And x plus 1 cannot be 0. And then we add 2 to both sides. We get x cannot be 2, and x cannot be, we would need to subtract 1 from both sides. We see x cannot be 1. In fact, negative 1. And in fact, where the funky behavior of the graph occurs is at negative 1. And if you try to plug in 2, you can see some funky things are going on with the graph. And we'll explore that later on in the term. So you're usually going to be asked to put this in interval notation, and here you have two values that x can't be, but x can be anything else. X can be an element of, so anything means it's going to run along the interval on the x-axis. It's going to run from negative infinity to infinity. but it's going to jump over these spots where x is 2 and x is -1. So we say, hey, start at negative infinity, let x be anything it wants. But when you get to -1, don't include it. So we use the open parentheses to exclude -1. We don't use the square bracket, which would include it. And then we go union. And then we say, hey, it's okay for it to run from -1 to 2. It just can't be -1 and 2. So I do that interval in parentheses, union, and now I say once you get past 2, you get to run, the graph gets to run all the way to infinity. So I wind up getting the union of 3 intervals where I exclude in interval notation the things that I cannot let x be because they would cause division by 0.